Okay guys, I asked you yesterday to have a look at once you've done some plotting of parametric equations, to try and plot cos t sine t. X is cos t and y is sine t. You plot pairs of values out, you plot them on points, and what you find is you actually get a point here, second point is there, third point there, fourth point there, fifth one here, sixth one here, seventh one at 0, -1, and eighth one is just about here again. What you should realise is, if you really need to, you can fill in other numbers, but this is forming a circle. Okay, so I had a follow-up question. What's the equation you know for a circle? From P2, apparently you should recognise x squared plus y squared is equal to 1. Now if we take our values, the x and the y, we do cos squared t plus sine squared t. Yes, we're always going to get the value 1. So that gives us a nice little play about that we can do to sort out our equations. Now, I'm not sure if you're aware of the more general form of this, but let's play about with what happens if we double the y. Now, I'm going to do this using GeoGebra. Put the equation in. And if I do 2 times the cos, let's start. What you should find is it actually goes out to being an ellipse. Now this one's going from -2 pi to pi. Let's just reduce that down to 0. Just show I'm not really. So there we go. We've gone all the way around. And why is that? Oh, I see. Yeah. They were doing -2 pi to pi, so you didn't see everything. But this is only filling in between 0 and pi over 6. Other thing you can do, we can do things in the y direction. If I add 1, you're used to y sine t plus 1, we'll move everything up by 1 square. Yeah, still happens. What might surprise you is what happens when I do the x direction. If I add 1 to the x direction, for years you've been getting trained that it moves the graph the wrong way. And this actually will give us an illusion as to why. Because what happens is, if I add the numbers on the parametric, it moves it in the right direction. The scaling happened in the right direction. So if I do this to 3, if you remember when you adjust the x value when you're looking at Cartesian equations, to make it go longer in the x direction, you divide by 3. This one, you multiply by 3. It's actually more logical. And the reason is, we're going to use these functions to substitute in to make us something going on. So let's look at what happens when I do x of t is 2 cos t, and y of t is sine of t. Now, to turn these into Cartesian equations, what we have to do is we have to think of some way of linking the t parts, either to get rid of them, which often doesn't work, or using a trig identity. So we need some form of link that will allow us to create an equation where we can replace things. Now, this one fairly straightforwardly, you should recognize, we're going to use cos squared t plus sine squared t, and that must equal 1. So I need the cos squared to be written in a form to go in there. So if we take that equation, cos t is x of t, or x, my x coordinate, over 2. Y of t, sine of t is directly my y function. I substitute them in. What I get is, I get x squared, x over 2, all squared, plus y squared is equal to 1. And you've just seen in here now, by transferring this to this side so I could actually get this cos t, that's where my halving has come in that you normally get to make these things scale. If you're not familiar with the general form, i.e. there's two general forms you need for an equation, Cartesian versions of a circle and ellipse. The circle is x squared plus y squared, and effectively this is r squared. If you can actually get this to the point where you've got x squared plus y squared over r, you get a simple equation that we can now adapt for what happens in this case. We've actually got, when we look at the graph, take a copy of that graph, not that one, that one. So this was back when this was 2, this had no number in it, and that had no number in it. Okay, so I'm just going to take a copy of that so we know what's in the diagram. And what we actually have is, instead of r squared, what we can do is we have x over, and this was a 2, which is the 2 squared. So this is x squared over a squared plus y squared over b squared. And if that is equal to 1, we get an ellipse. Okay. So that's the Cartesian equations for the coordinates. And what we have in the parametric form is there's my a times cos t and b times the sine of t. That tells me how that's stretched in that direction. And it's this that causes the division, is that moving these around so that we can get the t's into our equation. Okay, so let's move on to the examples they've got.